They gave y'all Apple Pens?
Yeah.
Wow. That's cool.
Yeah, so I forgot my password. And I managed to, in the process of trying to use other devices to start it up, almost eliminated everything I had. So we were on the phone with Apple for about an hour on Saturday.
Oh no.
I'm doing a morning's worth of tragedy. So in the end, we wiped the iPad clean and started it all over again.
Wow.
RP, you can use your fingerprint as a password.
You know what? The first time you use it, it won't let you. It does face recognition, and I'd gotten that all set up. But the first time it comes on, it wants that passcode. After that, to restart it and so on, you can use your face recognition. Well, anyway, you guys all set for the exam tonight?
Yes, sir.
Good. We don't have to do anything today then, huh?
Cancel class.
Cancel the semester.
We're almost done here. What, 5 more classes? A couple of tests, and we're out of here. I sent you all guys, sent you something about looking for jobs. This was came from a guy who sells opportunities to have internships. That's how he makes his living. But he also talks in general about jobs and so on. And he's absolutely right. As bad as the news sounds, the jobs for you guys are really out there. There may be a short delay in getting them, but as soon as things ramp back up a little bit, everybody was scrambling to find people with degrees, especially advanced or technical degrees. And you guys are in that sweet spot. So look at it as a great opportunity to find a niche where other people have given up looking. And his point is that the small and the medium-sized companies know they still need somebody. The big people, they're struggling with huge numbers. I mean, Disney may need you, but they have to lay off 100,000 people right now, so they don't know what they're doing. But a company with 80, 90 people, 6 or 7 of them technical, they're looking for somebody like you. So it takes a little bit more work to find those jobs, but they're out there, lots of them. All right, so we're going to be talking about, well, you're going to have a test, a little bit on diodes as detectors. And then we're going to talk about nuclear structure and nuclear properties and radioactive decay, and then the technologies that come from that, good and bad. So here are the homework problems that were assigned that are relevant to the test. And then we have also the in-class problems that we did, including the use of the spreadsheets. Any particular problem that you want to start with?
All right, let's go over one with diodes.
Well, so with diodes, I'd give you the diode equation. You know everything that's in there, right?
I might have to brush up my memory.
Yeah.
Quite a bit.
So you look over that equation and make sure you understand what it's talking about. But
Okay.
how do we use diodes in as detectors, especially for radiation? Alpha detectors, beta detectors, and so on.
Use a photoelectric effect.
No, not really.
Chris, David, that's your area.
That would imply that we're using, well, not necessarily, but for diodes, probably that we would be using light. Now the gammas, they will have they will do a photoelectric effect. But what kind of diode are we talking about when we talk gammas? Any idea?
Something like a transistor.
No, it will be a regular diode, but it'll be made out of germanium and very lightly doped germanium. So how do you use a diode when you're going to detect with detect radiation with them? And this little circuit right here is kind of the hint.
So it's gonna work like a photodiode. Was there there was a photoelectric effect, right? It just would hit some germanium atoms, excite some electrons, and then you would have an electric current.
So you could have anything that will create an electron hole pair you can detect with a diode. But you have to bias the diode properly. How do you do that? If you only, let me go back up here again. You notice radiation's coming in here and producing an electron hole pair. So what are you detecting when that happens? And I don't mean the thing coming in. I mean, what's the detector detecting? Charge. Or current, however you want to look at it. The electrons, as they've got this bias, so you've got your high potential over here, you've got your low potential over here. You create an electron hole pair, the electron's going to go this way, and the positive charge is going to go this way. Don't they just cancel out as far as current then, since they go in opposite directions?
No.
Why not?
Doping?
No. If only electrons move and they move to the right, which way is the current flowing?
The left.
To the left. If only positive charge flows to the left, which way is current flowing?
To the left.
So if I've got electrons moving to the right and current to the left, both of them are creating a current to the left. That's because the current is proportional to the velocity of the charge. So a negative charge times its velocity times the number of charges moving per second is the current. So this is negative, but so is its velocity. So the product of those two is positive, just like the positive charge and the positive velocity for the positive charge, the hole there. So when I create an electron hole pair, if I've got the diode biased, then I can collect all the negative electrons going to the right and all the positive holes going to the left. And I have a net current that's not zero. But what does a diode normally do? Doesn't it just conduct? And if you put a bias across it, wouldn't there be a current there already? And a current in a diode, even a few milliamps, involves the motion of 10 to the 23rd electrons. How are you going to detect an extra 1 or an extra 2? So how do you run the diode? Backwards. So this is actually a little different. This is called a PIN diode. Let's just not pay attention to the insulator part of this. This is the N-type material, and this is the P-type material. Normally, what voltage do you put on the P-type to make it conduct? High potential or low potential?
Could you repeat that question, please? I'm sorry, I was writing some down.
Yeah, let me move over to the whiteboard here for a second. Okay, so I've got a PN junction here. And what makes this a P? What makes this material right here P material?
Does it attract the positive charges?
The holes. If this were silicon, what kind of material in there is making it P-type?
They have one less electron.
Accepts. Right, they've got 3 valence electrons instead of 4. And so I have the absence of a bonding electron. I don't have an absence of charge, I have an absence of a bonding electron. So we call those holes, and they behave like positive charge. And what do I have over here on the inside?
Negative holes, basically. Well, the
Electrons, yeah. That's
holes, but
electrons.
there you go.
So these are elements over here, extra elements, and it's like 1 out of every 100,000 or million silicon atoms is there an atom with only 3 valence electrons over here. And over here, it's typically 1 out of 100,000 atoms or 1 out of a million atoms have 5 valence electrons. So they come in and 4 of them fill the chemical bonds that the electrons, valence electrons in silicon were filling. And then there's 1 left over, and it is barely sticking to its parent atom. And by barely, it's like 0.03 electron volts of attraction energy. So it's basically they're free electrons. So I need to connect this to a battery. How do I do it? I want current to flow.
Wouldn't you have like the positive terminal on the left and the negative on the right? I'm sorry, the other way around, right?
So like this.
That is what I am saying.
Okay. Now, if I were to draw the circuit symbol for this, what would it look like?
Oh, it's a circle with a triangle in the middle, right?
Yeah, kind of. Let's leave.
Yes, sir.
Let's leave the triangle out. I mean, the circle out. So
But I wish I could draw it. If you see my pencil,
It's like this. It's like that.
Yeah, that's yeah.
like this.
Yeah, but I put a circle around it. Yeah.
Okay. Well, we don't need the circle,
Oh,
but this is okay. They do that sometimes. Is that a diode symbol right there?
you need a line, like you know what I mean? Like I don't. Can I draw it? Do I have? I have a pen here. Could it be like this, like that?
Hey, how about that? It works.
Yes, sir.
Oh, dude.
Oh, yes, sir. Oh, wait,
Yeah.
here, I'll erase it.
There you go.
Okay. Well, that's neat. That worked. Okay. Did I draw it correct?
That is 100. Well, in the line a little bit small. I mean, yeah, that's. I'd say that's perfect.
Okay. Is that equivalent to this?
Would you need it to be backwards?
Ah, yes.
Ha.
And what does that arrow tell you?
The direction of current, right?
Yeah. So have you got your battery right?
No. Yes. You would need the positive when you need the positive to be on the left.
Yeah. So the current flows from high to low potential, and current flows through the diode the way we said. All right. That's a good little bit of information to have there. Now, lots of current flows. Lots of current. And the fact that it's, say, 6 milliamps or even 6 microamps. Or nanoamps or picoamps, it doesn't matter. There are so many electrons moving that the actual number of them has a statistical variation that you're not even going to notice. You would have to have an ultra sensitive piece of equipment. And you could think hundreds of thousands of dollars or millions to get that kind of sensitivity. How are you going to detect one or two electrons due to radiation with all this stuff going? You're not, right? The variations will be bigger than your events. So what do? You don't use it in a conduction mode. So the only way I can do that is to go back to my bias supply and make it backwards. And what's that called? What kind of biasing is what we mean by putting a voltage on something. So what kind of biasing is this?
Reverse
Reverse
biasing.
bias.
Yep. Can't spell this morning.
So Dr. P, did you say that reverse biasing can help us to detect like single electrons?
Yeah, so here's what happens. You've got your high potential side here, and you've got all these electrons that were there ready to be part of the current. Well, they all leave. And you've got the low potential over here, and all these holes leave. And what you've got then is a depletion region. There might be a few holes and electrons left, but they're going to be wanting to leave, and you're going to have this region where you're conducting electrons and you're conducting holes that are available to be current are gone. Now, when you can bias it completely enough so that even all these are gone, and that usually requires a larger voltage. You've got to take this voltage up a good ways. For some detectors that we're talking like Chris, are you here? He's not here.
Yeah, I'm here.
He's on mute, probably.
I'm here.
Yeah, so what voltage were you using on your PN junction, your surface barrier detector?
65 volts originally, so 70. I think when I did the calculation, I messed up. So when I did it, it was actually ended up being about 71 volts.
Okay. Now I have detectors in there that are much bigger than Chris's, and Chris's the size of your PN junction was, I think, about a millimeter thick.
Yeah.
And I've got a germanium diode that's about 5 inches thick. That would be 12.5 centimeters or 125 millimeters thick. And I have to, in order to clear all the electron and holes out of this thing, whereas Chris's took about 65 to 70 volts, this one takes about 2,000 volts.
Jeez.
And I can buy them bigger. And it's that large size detector that you use for gamma ray detection, because the gamma rays interact so weakly with materials that a junction like the one that Chris was using, they'll just go right through it. They might have an event once in a while, but not often. And in order to cut down on the statistics on these big detectors, we run them at liquid nitrogen temperatures. Chris's could have run his at, say, about minus 20 degrees C, where this is 77 Kelvin, which is about minus 200 degrees C. He could have run his a little bit, and so when he was looking at peaks that look like that, they might get narrower like that because of the statistical variations. But the most important thing is running reverse bias and running the system so that you have a fully depleted detector. And then this is your detection region. And anytime a particle or radiation comes in and creates an electron and a hole, sometimes they'll create electrons that then go around and make lots of electron holes. The holes get swept out this way and the electrons get swept out that way, and you can either put it on a capacitor and measure the voltage across the capacitor, or you can run it through an ammeter and measure the current through the ammeter. And since it's an event, you'll be measuring a voltage pulse or a current pulse. And that's how we run most of these detectors. We talked about some, like the Geiger counter or the similar type gas detectors, where you can integrate the charge, or you can charge them up and watch the charge go away. You could use the charge created in this kind of detector as a way to discharge something and measure the change. So a lot of different variations, but with the diodes, it's always the reverse bias to get a depletion region. And so the diode equation that you look at is really telling you more about the forward bias than it is the reverse bias. And if you want to treat these things ideally, then you just look at the current created in the reverse bias as your total signal for the detection. So PN junctions, what can I dope the silicon with to get p-type?
Anything with 5 electrons?
Give me an
Germanium?
example.
Oxygen.
Oxygen is a notoriously bad choice. Oxides.
Arsenic.
Pretty par for the course.
Pardon?
Pretty par for the course for me.
Arsenic.
Arsenic? How about phosphorus?
I think that's good too.
I'm sorry. Aluminum. Is it aluminum right next to silicon in the periodic table? And boron. And so anything in that column next to silicon on the left works. What about making N-type silicon?
Anything in the column to the left or in the other column?
The column to the right, so phosphorus. And what else is in that column? If you've got your textbook, there's a periodic table on the very back. So arsenic would be, yeah, arsenic, that's what I was thinking, is N-type. So it goes down here. Boron, aluminum, gallium. Gallium is often used with silicon. And phosphorus, nitrogen is not used that much with silicon, but phosphorus and arsenic are. So how do you bias germanium then? What are the valence force semiconductors materials? Silicon, carbon, germanium,
What is SN?
N.
And
And what's the last one? Lead. Which of those do you recognize as real semiconductors?
Silicon.
Silicon and germanium. Carbon is notoriously difficult to dope. The atomic density is so high that doesn't make room for anything other than nitrogen or sometimes boron. And they don't work particularly. The nitrogen is not a good dopant in carbon, although it does work. What about tin and lead? Well, then it's up there lousy metals. And what happens in that column, the band gap for carbon, and you understand what band gaps are?
Yep.
Okay. So the valence band and the conduction band. For carbon, it's about 6 electron volts. For silicon, it's about 1.2 electron volts. For germanium, so 6 EV, 1.2 EV, this is about 0.5 EV. These are metals. They don't have a band gap. Their conduction band gap overlaps the valence band gap, but not well. And they're really not good electrical conductors, but they're metals. So the semiconductors, this really acts more like an insulator, and these are the two semiconductors, and then these become metals. All right. Let's try a problem here now, separate from these. There are just a few problems related to detectors in this chapter, and a few on the band structure and the meaning of that. You should take a look at those. Let's go into our structure, nuclear structure. How's the nuclear structure laid out? We've got protons and neutrons, right?
Yeah.
So if I give you something that looks like that, what can you tell me about? What can you tell me about that? What is that?
It has 60 protons.
That's 60 protons, right? And
Would it be like element 60?
it would be element 60. What is that?
Let me pull up the trusty periodic table. Neodymium.
Neodymium.
Indeed.
Yeah,
Neodymium.
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 And what do we know about neodymium now?
It's a rare earth. It belongs to a lanthanide series.
Actually, just from this, what do we know about it?
Oh. We know that it has 60 protons.
Okay.
I guess would it have no? Actually, I don't know.
It's got 60 neutrons too, right?
Nope, it's got none.
Yeah, that's what I. Yeah, that's what I was. I didn't want
I
to.
just wanted to see
here
if
on
you
the
light
bottom.
on this or not. So this would be mass 60 neodymium.
That's gonna
That doesn't exist.
I want.
I have a question. So, like, if the Z number is 60, how is the A number 62? You know, like,
Yay. Oh, you
Well,
got
this can't exist, can it?
yeah, not cannot, no.
Whiteboards.
So this is the atomic number, and the difference between these two is the number of neutrons. So I gave you a isotope with no neutrons. Okay, so we know that doesn't exist. So let's go to something more realistic.
That was a trick question.
Yes, it was. 145. Now what are we talking about? You're talking about element 145?
No, it's still
Element 60.
neodymium.
So it's still neodymium.
Imium.
What else do you know about it?
It has 145 protons.
No, it has.
No,
60 protons.
Yeah.
60 protons.
Yeah.
There's 85 Newton.
And 85 neutrons. And then what does 145 represent?
The mass number.
The mass number.
Number, which is the number of protons plus neutrons. It's not the real mass, it's just the mass number. Okay. That's vocabulary. And if I had, let's see, let me get rid of that. So this is neodymium 145. What if I had neodymium 144? What are these two elements called?
Isotopes.
Isotopes. P means the same number of protons. What's an isotone?
Different number of no. Different
Oh,
number.
it's isotope.
Same number of neutrons.
Wait, same number of neutrons?
Yeah.
Different number of protons?
So if I had,
The two different elements can be isotones.
let's say I had promethium. And it was promethium 143. It's an isotone with one of those two neodymiums. Which one?
Wait, what was the question? Sorry.
Okay, so I've got two neodymium isotopes, 145 and 144, and I bring promethium 143 in. It's an isotone. With which one of those?
Neodymium 144.
No, yeah,
these two have the same number of neutrons, don't they?
Yeah.
Promethium is atomic number 59. All right. If I gave you on a mass energy scale, where Z goes this way, can you tell me what kind of decays are doing this? And what kind of decays are doing this?
Beta plus and beta minus.
Yeah, which is which?
Beta plus is beta plus would be the one coming from the right to the left, right? Because it emits a positive. Yeah.
Are there some competing processes for these beta? Is there a gamma or an alpha on here that we could deal with, or?
There could be like if there's excited state of that bottom line, then there could be just gamma decay down. If that's what you're talking about.
If there was, yeah, there could be, but there isn't, is there? It's not as I've shown it.
So, what are other competing decay mechanisms that might
Yeah.
occur here?
Yeah.
I mean, alpha.
Would drop the atomic number by 2 and would have a huge mass energy change. So it would be more like something way up here decaying to something way down here. Because you're throwing out 2 protons and 2 neutrons, so atomic mass changes by a gigantic amount. How about electron capture?
Won't that usually occur with the beta minus or both?
No, so if you've got your nucleus here and you've got your electrons orbiting it, electron capture is where it takes an electron and combines it with a proton to make a neutron. So in the end, what's happened to your atomic number? Increased, decreased, or stayed the same?
Decreases. If it
Decreases. We changed the proton to neutron.
Right? It makes
So
it
that's
decrease.
this process right here, right? Isn't this decreasing atomic number?
Yes.
This electron capture competes over here. Okay. And we had a shell model structure with all those 1Gs and 5Xs and so on. What are those? What is that 1G, for instance? What does the G stand for?
Gram.
No,
No.
I'll change it. 1H.
Planck's constant.
No. the,
To be honest, I don't know.
the orbital. Allah?
I don't know. Yeah, maybe.
Hey, Lisa said something.
Wait, the L value is it the angular momentum value?
The orbital?
Yep. Okay. And then we had parity. What was parity about?
It's like odd and even numbers.
Odd and even numbers for the L. And it has to do with whether the wave functions are symmetric, meaning they look like this, or whether they're anti-symmetric and they look like that. You notice if you flip things, this side becomes positive and that becomes negative. If you switch around the center here, nothing happens. Here's another, so we call this an even, and we call this odd parity. And so I could have one that looks like this. Is that even or odd parity?
Would
With respect to the center line, is this, it should go through the center, is if I flip this thing 180 degrees, would it look the same or would it be upside down?
upside down.
Upside down. Whereas this one up here, if I flip it, it will become reversed or upside down, however you want to say it. So this is the odd parity, and this is the even parity. And it ends up that evens have a plus and odds have a minus, and the parity is -1 to the L, or to the sum of the L's if you have more than one particle involved. So the states that we might talk about up here, a number of them, of the states are all even nuclei. So they almost always have a 0 plus. I'm sorry, they always have a 0 plus ground state. All right. Radioactive decay, if that's it, there's also the mechanisms of decay. And how do things decay?
Exponentially.
Exponentially. And what's T0 called?
Half-life. No. No, that's T1 half. When it was like created, like when it first started, I don't know, when the radioactive sample was made, that usually has a date on it.
Okay, so lambda is how we normally write it, and lambda is equal to the log of 2 over the half-life. And we talked about the meaning of that, how that tells us about doubling times and halving times. Because if it's growing exponentially, the only thing that changes is the minus becomes a plus. And so we talked a little bit about the meaning of doubling times and the growth. I think we talked about the city of Denver, as a matter of fact.
Did you write, is that a no right next to T naught?
In 0?
That was a response.
Oh, I was writing something down. I didn't. Sorry.
All right, what's the activity of an element?
What's the activity of an isotope or
How
element?
quickly it decays.
Yeah, or an isotope, yeah.
The decay per second, decays per second.
Yeah, it's the number of decays per second, so it's a derivative.
And just stands for number of decays.
And the definition of a derivative here is n at t plus delta t minus n at t divided by delta t. So if this thing is decaying, is dn dt positive or negative?
Negative.
Negative.
Negative, right. So we don't communicate it that way, do we? All right, what are the units of activity?
Per second.
Per second, that's given a name.
Free Burkwells or something.
Becquerel.
Becquerel.
Why is he known? What's he known for? He discovered radioactivity. But there's also the unit Curie, which is 3.7 times 10 to the 10 per second. Who's that named after?
Marie Curie.
Marie Curie, yeah. Okay. What does this, well, let's take this one. What does this have to do with that? All right, I don't know if you guys have a class now. We're a little bit past. So make the connection between activity and this, and activity and the number of particles. Okay, so there will be at least one discussion question on here, because we talked in general about things like reactors and bombs and stuff, and so I'll ask for some informed opinions about some things. All right, any questions?
So you're just gonna like email us the test and we'll scan it and
Yeah.
email it?
So at 6 o'clock, I'll email the test, and I'll give you a Zoom link at the time that you can log on, and then if we can just briefly go over the test, you can get started, and you've got a little over 2 hours, and then I want you to scan it, your answer sheet, and send it back to me by 8:15. But I'll be on the Zoom page the whole time, so if you have questions, you can just ask.
When is our Sewanee scholarship poster due Wednesday? It's like midnight.
Oh, hey, Hank.
Yeah, so I'll send out a note about that. I want to get together with each of you tomorrow sometime for about 30 minutes to go over your poster. So I'm free most of the day. If you can tell me, if you can get your poster to me in the morning and then tell me a time period in which you've got 20 to 30 minutes that you can spend, I'll try to put together a schedule. But if I need everybody to send their stuff to me by about 9 a.m.
Hey, David.
Wait, so you want to have posters at 9, and then we'll talk about them later that day?
Yeah, later that day. Just send me some times during the day when you're free to do that.
Can do.
And I'm going to send out an email and remind you about that.
David,
Yeah.
how's it going?
All right, guys.
Thanks, Dr. B.
See you later.
Thank you.
Thank you.